Okay, good morning, everyone. Welcome to the afternoon section. So our first talk will be Benjamin Basso. We'll talk about OPE and Wilson loops for form factors of local operators. So.
Thank you very much. So, I'd like to start by thanking the organizers for organizing this IGST in São Paulo and for having me here. It's a great pleasure to be back in São Paulo after so many years. So today I'd like to talk about some work that we've been doing with Alexander Tumanov. And there is a paper out already, and we are continuing with some follow-up. And this is a project that aims at understanding how to apply integrability in n equals 4 to the calculation of certain observables that we care about, and which are form factors of local operators. So let me first say just a few words of motivation, because we didn't have that many talks about scattering amplitudes during this meeting. I think we even heard by Istvan that there are no scattering amplitude in this theory, which is true. But okay, does that mean we cannot compute something? So the truth is that we are computing scattering amplitude with a small regulator, so we could do something like going to the Coulomb branch or something like that, just to regularize asymptotic states. So anyway, there is something interesting to look at, and one of the reasons we are looking at it is that n equals 4, besides being a wonderful setup for studying many things like ADS, CFT, quantum gravity. It's also a wonderful laboratory, theoretical laboratory for exploring, mathematical and physical properties of objects like amplitudes in massless gauge theory. And of course, what we have in mind in this setup is, for instance, perturbative QCD, so high energy QCD, so the type of processes we're interested in to make contact with what people are doing at the LHC, for instance. And the reason we like n equals 4, obviously, is because, it's a gauge theory. It's not that far from QCD when we just look at certain type of processes perturbatively. But it has a lot more symmetries, an abundance of symmetries. And here I mean, of course, the usual symmetries, like conformal symmetries, but also all the hidden dualities and, of course, integrability. And the symmetries pave the way to developing new methods beyond what was known before, especially at higher loops, for studying amplitudes at weak coupling and also at strong coupling. Okay. So what will be central to the discussion, to my discussion in particular, is the duality between scattering amplitudes and null polygonal Wilson loops. So to answer Istvan's remark during this talk, I would say that the question to what are amplitude in this theory, the answer to this question could be they are like secretly null polygonal Wilson loop. So here is a sketch of this duality that you must have seen many times. So it's a duality that map one object and amplitude to another, which is a Wilson loop with a particular contour, which is made of null segment, and it originated from the study of the sigma model as strong coupling. So I will be fast on that, but the point is that there is a nice symmetry, T-duality transformation, if you are familiar with this terminology, that maps the theory back to itself, but exchanging particles at the horizon, like someone trying to set up some scattering experiment at the horizon, with a null contour at the boundary. And the map is pretty simple, so the momenta of the particles are becoming the edges of this contour, on which is becoming some just a boundary condition for a string, okay, ending on it. And that is just a definition according to Maldacena of the calculation of a Wilson loop in this theory. So as I say, the momenta are mapping to the edge of the Wilson loop. And furthermore, this is not just a property of strong coupling, so it was first understood classically and then extended perturbatively by Nathan and Juan. It's also something that has been observed and understood at weak coupling in the planar limit. So the planar limit is very important, but as far as the Taft coupling is concerned, it is believed to be an exact duality. And there are many important works. And what it gives us what it's giving us is a nice set of coordinates, which are this point that specifies the contour, the cusp, the coordinate of the cusp, to parameterize or to analyze, to write down the amplitudes, and together with a nice set of dual conformal generator or dual conformal symmetry that constrain very strongly the answer. But what is perhaps even more important is the fact that it allows you to apply integrability to this object. So it's not immediately clear what it means to apply integrability to a four-dimensional S matrix, at least I don't know how, naively, but it's kind of clearer clearer. It's not something trivial, it's something that was understood by Pedro and his collaborators, but it's kind of easier to understand it at this level where we are dealing with a correlation function in a sense. A non-local correlation function, but yet a correlation function. Okay, so that is for the background, I would say. So what is very well understood and very well studied. What we'd like to do next is, it's also kind of not so recent ideas, but with lesser development, I would say. But what we'd like to do next is to extend this map to other quantities. And in particular, one of the most natural things to look at after scattering amplitudes are form factors. So just matrix element of local operator, local gauge invariant, single trace operators of the theory, and some asymptotic states of gluon, like for instance, I don't know, whatever, gluons or particle in this theory. Okay. And one thing that is immediately different and that we can see is that in the case of the form factor, for instance, the total momentum, so the sum of the p's, is non-zero. So there is no momentum conservation because, of course, we are breaking translation invariance. And instead, we have this Q, which is the total momentum of the process. And what it means for the Wilson loop is that the Wilson loop cannot be closed. So we are no longer talking about, like the usual, you know, gauge invariant Wilson loop, like the closed one. Instead, we are dealing with something that is a bit harder to define, but which has been proposed to be a periodic Wilson loop. So the idea is that you should, as before, define a contour using your momenta. It will not close because Q is different from 0. And so in order to get something that is cyclic invariant and a bit more, how to say, well-defined, you repeat it indefinitely. So you get this infinite train here, this zigzag of momenta, which are repeating forever in one direction. So this is a cartoon of the type of minimal surface that you would expect to find as strong coupling that will describe this periodic Wilson loop. And as I say, it's not immediately clear what it means to compute a periodic Wilson loop, even, well, it's not obvious. But there is, by now, a lot of evidence for this duality. So in particular, for the case of the form factor of the stress tensor and the vacuum expectation value of the regular bosonic Wilson loop, periodic Wilson loop. So there is some sort of prescription for how to compute this periodic Wilson loop, and when you do that at weak coupling, you can match it directly with results which are known from form factor. And what is especially interesting for us and for integrabilists is the fact that we can, once we have this Wilson loop, we can develop some integrable Bootstrap program similar to the one for scattering amplitude, as well as some very advanced techniques based on analytical properties of the answer. Okay. So, but in principle, we should expect this dictionary to be much more general and not to be only, I mean, applicable or meaningful for the stress tensor, which, okay, of course, is probably the most relevant operator in this theory. But naively, we would expect this mapping to make sense for any operator. So the problem is that Fernando and Juan, who first proposed this duality, did not provide a very strict map or dictionary. So instead, we have to rely on ourselves and to figure out what it could mean. Okay. So the idea again is that on the boundary, we have some external state, the P's, that is mapping to this contour. That is probably well understood. And at infinity, we get this string that is going all the way to the horizon and can possibly support some state. So the idea is that the local operator here will be encoded somehow at infinity by a state psi, and we have to figure out what this state could be and how to eventually use it to set up some integrable description. Okay, so this is for the big question, and this is what we've been trying to answer for a certain class of operators. Okay. So here is a rough plan of my talk. I don't know if I will have time to talk about everything, so maybe I will jump somewhere. But first, I will talk briefly about form factor of half VPS operators. Explain what type of Wilson loops we expect them to map to, and then go to integrability. And finally, talk about something that is more work in progress and very poorly understood, I would say, which is the case where we have an excited operator like Konishi, like a non-protected operator. So the part one is, so first we have to define this object. So there is some technology, you know, to take advantage of the symmetries of the theory, in particular supersymmetry. And one of the first things we can do is to put all the states together in a single superstate. Okay, so the gluon, gluon with positivelicity, fermions, scalars, everything we put in a single state. This way we can be more inclusive. And this state is a kind of eigenstate of several quantities, in particular the momentum. So it has a definite momentum, which can be written as a product of two spinor variables, so spinor helicity variables, which are more convenient than momenta. As well as some odd variables, some Grassmann variables that just enumerate the states. And with lambdas and etas, we can also form what is called the supermomentum, which is this combination here. Okay. So the simplest operators in the theory are the simplest single trace operator are the chiral primary operator and their descendants. So in principle, we should be considering all their descendants, I guess. But we are not going to do that because this formalism is very chiral in nature. So it likes more the Q supercharges, if you want, than the Q bar. So it's just more simpler to focus on the chiral Q descendant. So we just take the state, the chiral primary trace of some scalar field to the power k, and we act on it with a string of Qs, as many Qs as we can, and this way we get some chiral super multiplet, or I don't know, super field stuff. An example is a stress tensor super multiplet, which in this notation corresponds to trace phi square, and which has this well-known expansion in terms of Q descendant. So in this case, the operator is the fact that it's protected is manifested by the fact that this is a short supermultiplet that only goes up to theta to the 4, with this piece here being the Lagrangian. Okay. So in general, we'll have k to be arbitrary k, and that will correspond to operator with a scaling dimension k, obviously. For the form factors, we can do something similar. Instead of looking at form factor one by one, component per component, we can try to lump them together inside a super form factor. So in the same way that we do a Fourier transform to fix the momentum, we can do I don't know, it's called Grassmann Fourier transform to fix the super momentum, and this way get an object that is more easier to analyze. So for the case of half VPS operators, there is one thing that is important to keep in mind. So because the operator are annihilated by some supercharges, there is a certain so there are some supercharges that are supermomentums that are zero automatically, but we may in principle also have some twist, if you want, in the supermomentum of the other sector. Okay, so in the following, it's natural in the end to split the SU4 indices into SU2 times SU2, which correspond to preserved and non-preserved symmetry, if you want. And the Susy-wide identity fix the form of the super form factor. Essentially this piece here, which is just a big delta function or super delta function that is enforcing super momentum conservation. Okay. And the piece that we would like to identify with the Wilson loop, the piece that is the most interesting, is this factor here that remains after we strip off this generalized Park-Taylor factor. And this is a big polynomial in the Grassmann parameters. The simplest factor to look at is the one with the lowest fermionic degree, and it's the so-called MHV form factor. Okay. So in order to search for a dual description, well, we don't really have a map. We don't know how to proceed. So what we did in practice was to just look at the data and analyze the data in the right variable and see if they are telling us something. And here, in this case, the data is known. It has been a variable for many years already. And here is an example, for instance, of what we will get at tree level for the stress tensor or the k=3 operators for the MHV form factor. So the one with the lowest number of etas in the right-hand side. So these are formulas. They are known. Okay, you can generate them in many ways, like BCFW. And then you want to analyze them. So we don't expect to see a Wilson loop here in this formulation because we are not using the right variables. But in principle, if we go to the dual variable, we should see something happening. And here is a map in its full glory of what we have to do in order to go from momenta to coordinates and also super momenta to super coordinate of the cusp of the contour. Equivalently, we can just set the momentum super twisters, which is totally equivalent, and which relate by some simple linear transformation to the original variable eta tilde. And what we see happening is a simplification. So the main simplification is that the MHV form factors enjoy dual superconformal symmetry. So it's not the conformal symmetry in the original space-time. It is conformal symmetry in the dual space-time, okay, which is acting on the variable x and theta in a way prescribed by conformal transformation. To be precise, it is invariant under a certain subset of the full group of symmetry, because the quantity is only dependent on some sort of smaller version of the momentum twister in which the mu are absent here. So we only have the top part, lambda, and also half of the etas, okay, the ones that correspond to the nice SU2s. Okay. And the answer can be written, in fact, in a very compact way by using these building blocks, which are called R invariant. These are quantities that we can form easily and that automatically satisfy superconformal symmetry. And as an example, the three answers that I wrote before can be written as for any number of points in a single line formula like that, where we sum over all the certain set of R invariants. So there is a nice geometrical interpretation. It's similar to what happened in 4D. I won't spend too much time on it, but there is a nice way of thinking about this object as giving us the area of a polygon with the decomposition corresponding to a triangulation of the object. This is a so-called M=2 amplitude-hedron. And result for higher Ks generalizes also along the same line by using some higher K version of the 3 amplitude-hedron. So this is evident that this object really wants to be interpreted in a dual manner, I would say. So what is a dual object? So we expect it, as far as the contour is concerned, the Wilson loop is concerned, to be built out of the same ingredient as we are using for scattering amplitude. For super amplitude or super form factor, we need actually a super Wilson loop generalization that was proposed by Simon years ago, and which is based on a super connection that extends the usual bosonic connection, as well as some corner insertion that we need to put between every two edges to maintain supersymmetry and etc. So that part is, again, the same as for amplitude. There is no novelty here. Then for the dual state, this is where we need to be a bit more inspired, I would say. Because the contour, of course, is coming from the state, but now we have to represent the local operator. And so that means that presumably we should pick a dual state. So instead of looking at a vacuum expectation value of this periodic Wilson loop, we should look at some matrix element. Okay. And there is not much we know about how to pick this element, I should say, but at least there are two requirements that we feel should be there, so which are related to the fact that the state should be translationally invariant and also annihilated by the dual supercharges. And the reason is not some deep symmetry consideration. It is the fact that this translation and super translation symmetry in the dual picture are not really symmetries, they are redundancy of the parametrization. So they correspond to absolutely nothing on the original form factor description. So they should just drop out. They should just do not matter. And so if we go along this line, if we go down this line, then it appears that the simplest choice we can make to represent an operator which has a certain charge and ensure that it has zero momentum, to just build it out, of zero momentum scalar particles. So the idea is that this state here, for the case of interest here, for the trace phi to the k, should just be a collection of k minus 2 scalars at zero momentum. Okay. In particular, when k is equal to 2, there are no scalars here, and this is just the vacuum. Okay. So there are several checks we can do, actually, that verify that this is correct. I will skip it because it just confirms the analysis, and I don't have time, I think. 5 minutes, yeah, that's what I said. I don't have time. And we can also do a similar thing at loop level, and it's all working very, very well. So this helps us eventually to understand the way to bootstrap this object. And the construction is based on decomposition of Wilson loop in terms of pentagons. So if you've never seen that before, well, you will not understand it today. But the idea that we can write down some sort of OPE decomposition similar to the one we have for correlation function, except that they are taken over different space of states and using different objects which are these pentagons. What is nice is that this construction can be generalized almost straightforwardly to form factors. The only thing that we have to do is that instead of having pentagons, which are just following one another forever, at some point we have to cut the sequence, because it will start being periodized eventually, and replace it by a boundary state. So there is something at the end of the sequence that is absorbing the states, and that is supposed to represent the effect of the operator we are inserting. And we do have some sort of integrable bootstrap. So this is a part that is technical, but familiar to people doing integrability. So we have some sort of nice familiar equation, like the Watson equation and the crossing relation, that put constraint on this form factor that we are trying to guess. Okay. And one thing that is interesting is that these equations are very similar to the one we had for the pentagons. The big difference is the crossing relation, which in one case involves just a move by 2, while for pentagon it involves a move by 5. And I think we understood not long ago, but based on previous work, is that we could actually use some very natural building blocks that generalize the one we had for the pentagon, such as to solve for this axiom for virtually any type of polygon. So here's the polygon, just encodes the number of steps we should take to come back to the starting point. And all we have to do is to somehow twist or tilt by some angle the BES kernel that was supporting the pentagon construction. So this is an object that is similar to the one that was discussed by Didina and Zoli. We just have one parameter family of them, and we can write down some general formula for any sort of polygon. The drawback is that we have a solution, but no problem, because we don't know what this generalization describes in general. The two important exceptions, however, are the pentagons themselves, which we have, and also the form factor transition, which correspond to alpha is equal to 0 here. Okay, so in the last 2 minutes, I will present something more sketchy, which is trying to generalize this discussion to Konishi. So Konishi is the most relevant non-protected operator in this theory, and it's also a very nice quantity to consider if we want to establish a bridge between the spectral problem and amplitudes in this setup. And the question is the same as before. What is a state that is dual to the Konishi in the form factor setup? So first we have to define an object. So here there is no supersymmetry to take into account. So we just take the form factor of Konishi and we strip off some Park-Taylor factor, and what we get is what we call the Wilson loop. Okay. In fact, I'm cheating because it's hard to do that. So, but we have to simplify a little bit the kinematics and also assume that for some reason we are working with states, asymptotic states, which are not arbitrary but fine-tuned to obey a zero momentum condition. And if you don't like this kind of condition, well, too bad, we have to do it. But it's also equivalent to saying that instead of considering Konishi itself, we are considering the chiral top descendant of the Konishi operator. So this seems to be a good starting point to guess that Konishi is dual in this picture with a state made out of two scalars, two zero momentum scalars, but which are this time, you know, in a singlet combination instead of being in a symmetric product. Okay, and this is working pretty well. And you just do the math, and you get some nice compact representation. Then for any edges, in principle, it's relatively easy to do the calculation, which is matching perfectly the data. So that seems to be the right guess. But this isn't really the guess. There is a complete guess. So there is a kind of next to best guess, guess that we have to make. And that has to do with divergences. So there is a kind of mixing problem on the dual side. It's not the usual mixing problem related to UV divergences, because in the dual picture we don't have UV divergences coming from the local operators. But we have IR divergences coming from the states. This is what is important. And what we understood by doing some divergent analysis, some computation at one loop for various type of contour and Wilson loop, is that the state made out of the 5 bar state is not consistent by itself. It's not renormalizing only with itself, but it's also picking some contribution from the vacuum. So that's a bit unusual because, while Konishi is in principle the prime example of something that renormalizes trivially, here it isn't the case. So the next to best guess, which passed many tests, and allows us also to explore this duality at Konishi level, is to actually work with a linear combination of 5 by pair and the vacuum. Okay. So that's all I have to say for the moment. Of course, there are some big questions that remain. The most important one is perhaps to understand more systematically how to identify the Wilson loops for form factors. The way we did it is very sketchy. What is perhaps more interesting for integrability point of view will be to understand if we can find a general solution to the Bootstrap axioms, possibly in terms of QSE data that will allow us to accommodate for all these excited states that we expect, in particular Konishi. And here I'd like to mention that it may be important for us, I mean, in order to succeed, to have a better understanding of the QSE mu function, for instance, a strong coupling, because this is a regime where things become relativistic, and in a relativistic regime we can, in general, classify solution to Bootstrap axioms. And so if we knew what type of object we should be considering to match with expectation of strong coupling, we could perhaps come up with some reasonable guesses. And that connects with Simon-Stock and the progress at computing QSE data as strong coupling. And there are many other connections that would be worth exploring, like the one with the light-like limit of correlation functions. And there is a poster about it. Thank you. Sorry for being late.
Okay. Thanks, Benjamin, for the very nice talk.
Is there a simple way to understand why the operator after T-duality became a state at infinity?
Well, I don't think there is a simple way. That seems, it appeared to us as the most natural assumption. But perhaps there is something that could be living at infinity and will not be, I don't know, an asymptotic state. But the question is, how should we describe it? So this is directly connected to this understanding in a more systematic and profound way what the duality should look like and how to go from one to another. So we are really doing like guessing. So.
Would it be useful to think, say, there is this gross mass, right, where you have the minimal surface and you can T-dualize and see a polygon?
Yeah.
maybe one could do gross minus plus a closed string, individualize that configuration and see what you would get.
Yeah, so that could be, but maybe we can explore, yeah, starting from something which is better understood and try to take some limits. So in this sense, what could be interesting to look at is this, correlation function of two zigzag Wilson loop. This is for this double trace contribution to the amplitude studied by Amit and Alex and collaborators. And then in a limit where they are very far away from each other, there should be an expansion that corresponds to this form factor expansion. But I think it's just not studied enough, to get a very clear-cut understanding of what is happening. So,
thank you.
I did not have the answer anyway to your question.
Or maybe just then one more question. So you had a slide where you had a bunch of polygons, of different polygons, and you said that we could actually solve these axioms.
Yeah.
Because I remember when we were discussing pentagons for the first time, pentagon was important because of
Yeah.
SU4. So that now you understand it's not the case. You could generalize it.
So we have building blocks. We can put them together in a way such as to solve crossing for any polygon. And it seems to better, as good as for a pentagon. But okay, for pentagon it's matching something that exists in this theory. For the other geometry we don't know yet.
Would you expect that the large spin limit of hexagons should match with these hexagons? Or
if you could find some utility to what we are doing, yeah, it would be great. I don't know, yeah.
A bit of a technical question. So why is the highest weight in the multiplet has the simplest form factor?
Why is
you are concentrating on the highest weight of the multiplet.
the superconformal primary, you mean? Or?
Yeah, I guess it's something
sorry, by highest weight you mean this top descendant.
the top descendant, yes.
Yeah.
Why is it
This one
simpler?
here? Because somehow we could not make sense of the data that we have on the dual side if we are not in this sector. So if we are not in this sector, the Wilson loop is not exactly periodic. There is a twist. So each time you move by one period, there is some of the fields that are living on the Wilson loop are twisted a little bit. And then when we try to do computation, with the usual prescription for this twisted object, what we get is just meaningless. Well, I'm a bit exaggerating, but it's just not matching anything we expected. So we have to, in some sense, restore the periodicity, which amounts to imposing this zero supermomentum condition. And we don't know yet why we have to do it. It looks like a technicality, but it seems that it could also be more profound. I don't know.
Any more questions? If not, let's thank Benjamin again.
Thank you.
Very nice talk.